So hello everyone again and welcome to my channel. In here we're going to be looking at the alkylation of our allylic alcohol, and this is the particular compound, and by alkylation it means I'm going to add an alkyl group to this particular carbon in here in order for we to form this particular compound. But hey, during this particular reaction, we actually explore a specific type of a sigmatropic rearrangement, which is called the 2x3 sigmatropic rearrangement. We'll focus more on that as we explore these 4 steps in here. And one important thing we need to take note of is the interesting sulfur chemistry that is present in here. Sulfur is a really non-stable atom, and the stability is actually due to the oxidation states that it actually has. Like for example, it can exist as sulfur 2, it can exist as sulfur 4, or it can exist as sulfur 6, and it will still be able to stabilize itself when it's actually used in a specific chemical reaction. So let's jump into this particular reaction mechanism, and in our first step we are subjecting our allyl alcohol in here to a sulfur chlorophenyl group over here. And what happens in this case here is that our sulfur chlorophenyl group will actually be subjected to a nucleophilic attack from this particular oxygen here. And what happens then is that we have a leaving group, which is chlorine, and what results in is the formation of an alkyl group, which is attached to a double bond, and this is attached to oxygen with a positive charge here, and over here we do have our sulfur attached to our phenyl group. Now, since pyridine here is the base, what happens here is that pyridine picks up this particular proton, and what happens is that this particular compound becomes deprotonated and the oxygen becomes neutral to form this particular sulfonate ester that we have over in this particular region. Now, take note that this particular ester, which is a sulfonated part, is actually unstable, and therefore in order for we to stabilize this will actually undergo an sulfonate ester rearrangement on the presence of heat. So second step is, if I subject this to heat, it will perform a rearrangement that will actually enable it to undergo a 3 or 2x3 sigmatropic rearrangement. So in this particular case, our sulfur, which has lone pairs, will actually form a sigma bond here with this number 3 here. By numbering this is 3, 2, 1, 1, 2. So this is a 2x3 rearrangement. This will form a sigma bond here, this will reform a double bond, and this here will actually cleave off, which is a sigma bond, to form a double bond. So as a result of this 3x2 rearrangement, what we get is this particular product. And take note that this particular product has a similar structure that I'm going to redraw in here, which is equivalent to that which we have. Now take note also that with this alkyl group that is being generated in this particular region, there is a hydrogen atom in here, and this hydrogen atom is an acidic proton due to this particular double bond present in here and the sulfur attachments closer to this particular carbon, making this hydrogen here to a much more of a better acidic state compared to the rest of the protons here. Thereby, if I subject this to a use of a base by using this particular RBR here, what happens here is that there will be 1, the base comes in first, or I will say in this case butyl lithium. I can use it here with a negative charge, and we have lithium first. This butyl here actually attacks this particular part and removes this particular proton, thereby forming a case where this particular bond actually, which is actually initially a negatively charged carbon, then attacks this particular R group, and then what happens then is that this bond between the R group and the bromine becomes a lone pair on our bromine in here to form a negative charged bromide, and it will interact with this lithium positive in here to form lithium bromide, while on this other side we have butyl here, and on the other side we have the attachment of an R group in this particular carbon in here. So what we have is the formation of this particular compound that I'm going to draw right now with our two R groups, and in here we have an allyl over there. Now this is actually a good way to make an allylic sulfur oxide in this particular state. Now this that will be generated can actually perform a reverse sigmatropic rearrangement. So if I redraw this in here, with the sulfur and the oxygen here, and we have our two R groups in this particular carbon, and in here we have our double bond in this region. If we do our number system, what we see is that we have our 1, 2, 3, and 1, 2. So in this case, I'll reform my sigma bond here, and in here this will be the breakage of our sigma bond. So what happens here is that while this particular pair becomes a sigma bond in this region, this forms a double bond here, and this forms a lone pair on this particular sulfur. And what I have in this particular step is our 2x3 sigmatropic rearrangement that leads to the formation of this, which is also equivalent to this particular structure. Now, what we can do here in our final step is that we're going to have this particular phosphorus methoxide or methoxide in here, and what we have is a case where, actually let me rewrite this because this is a bad notation. We'll make this a 3 that is outside. So we have 3 of these attached to our phosphorus. So what we have is that it actually performs a nucleophilic attack or a SN2 substitution, where this R group, which I'm going to redraw here, with a double bond, the oxygen, we have a sulfur, phenyl, and in here we have our phosphorus with this over there, and what happens is this attacks our phosphorus, and this actually cleaves off in here, and what we have is a negatively charged oxygen after this process has actually taken place, with our phosphorus being positively charged, and Me3 with a sulfur, and this phenyl group with our other segment that is being generated in here. Now take note that this is actually in a particular solvent system, like for example we have methanol present, or we can have ethanol present. So what happens here is this oxygen, which has a negative charge on it, will pick up a proton, and then this will actually form our final product, which is what we have over there. So this is a good way by which we can actually perform this alkylation of our allyl alcohol 1 by using sulfur chemistry to actually help us to generate some of our intermediate, and also using an 2x3 sigmatropic rearrangement, either in a reversible or an irreversible way, to actually promote the formation of this our final compound. Thanks for following me through this. Truly appreciate it. Hit a comment down below, let me hear your thoughts, and see you all on my next video. Peace, love you all, and be smart.